We have seen inverse Laplace transformation methods on how to take inverse Laplace transformation of functions that are in S, converting or transforming them into functions of t. We had seen from how we do it by partial fraction method, which is the most common method, and then we had seen certain methods like Laplace transform of ft by t is what it is s to infinity integral of s to infinity fs ds, and many such techniques. Now we'll see one more technique that is a very important technique in getting the inverse Laplace transform. It is basically a theorem. It is called convolution theorem. What is convolution theorem? We will see. Let Laplace transform of ft be fs and Laplace transform of gt be gs. Then from here we get Laplace inverse of fs is ft and Laplace inverse of gs is gt. So if these notations are clear, if we have this thing, then as per convolution theorem, Laplace inverse of fs into gs is given by integral of 0 to t fu g u minus t du. This is also written as f star or asterisk g. This is called convolution. F convolution g, or it is also called faulting. So this is f faulting g. This is a very important theorem whereby we are able to get the inverse Laplace transform. Why? Many times you have seen we have a big function of s, function in s, that is to be transformed back to the ft form. There we can break it into two functions and do the convolution theorem, apply convolution theorem on that function and get the inverse transform. Let's see how. We'll see a familiar question that we had solved in the last chapter, and we'll solve it through this method so that we are able to understand the difference between the two methods. Now how this method is so useful. So let's start with that. So if you remember, we had seen this problem. S Laplace inverse of this. It was 1 by 2a t sine at. This we had seen in the last chapter. How we came to this result? We had seen that Laplace transform of ft by t is given by, so not Laplace transform, Laplace inverse of this is given by s to infinity fs ds. Sorry, not inverse. So Laplace transform of this, Laplace transform of ft by t is equal to s to infinity fs ds. We had put this s to infinity s by s square plus a square ds. I am rewriting it so that things become very comfortable for you. We had taken m equal to 1 by s square plus a square, so that dm was 2s by s square plus a square whole square. From there, after putting the values, what we had got was that ft is given by 1 by 2a t sine at. When we had taken the inverse Laplace transform, this we had got. Ft was 1 by 2a sine at, and therefore ft was into t. So 1 by 2a t sine at. The same problem we'll solve it by convolution theorem. So we can take these functions as s by s square plus a square into a by s square plus a square, 1 by a out of this. So now these are two functions. This is convolution of this and this function. Ft of this function is, we know very well, it is cos at, and ft of this function is sin at. Therefore, by convolution we get this is 1 by a. So 1 by a 0 to t cos au into sin au minus at dt. So what we do? We take 2 here, 2 here. So this is twice cos a sin b. That will be sin a minus b minus sin a plus b. So this is equal to 1 by 2a sin of au minus au plus at first minus sin of, this is not bracket, this is integral 0 to t, sin of this plus this, that is au plus au minus at dt. This is equal to 1 by 2a sin of au minus au, this is sin of at minus sin of twice au minus at dt. So what is this? Let me rub it. So this is equal to 1 by 2a sin at. It is minus cos at by a. This is the first. Second, again sin, so minus minus plus, this will be cos 2au. Oh no, sorry, this is not cos at. Sin at is constant because this was du, not dt. So the derivative, this is du. We are integrating with respect to u. So sin at is a constant. So this will be du. So u sin at. This is the first part. Second part is cos 2au minus at by 2a, because 2 is the coefficient of u. This is 0 to t, and where we will be applying t? Wherever we have u. So this is 1 by 2a t sin at. Here when we put t, this will be 280 minus 80, that is cos 2a, sorry, not 2a, cos 80 by 2a. This is the first part. Second part, minus, this is 0, so this is 0, and then when we put 0 here, u0, so this will be cos of at by 2a, minus cos minus theta is cos theta. So we see this cancels, so the answer is 1 by 2a t sin at. It is same when we had integrated it from s to infinity, taking Laplace transform of ft by t, the answers are same. They have to be same because the answer cannot be different, answer will be same. But this is the second method by which we were able to take out the result. Many a times when we have long functions, this method is more useful than the previous one. Also, the previous one we could apply only because that was ft by t of some function. So we were able to do it. Convolution theorem, whenever we have multiple functions, we can separate it into two functions and then integrate it as we have done here. So do some exercises from your textbook and you will be very comfortable.